far beyond the familiar boundaries of our solar system, in a serene corner of the constellation Leo, a subtle shift in infrared light arrived at Earth after journeying more than 120 years across the void. To the untrained eye, it appeared as merely another influx of data, one more cascade of information amid the vast archives gathered by humanity's premier orbital observatory. Yet concealed within that light lay a revelation that defied every expectation. A chemical imprint not born of barren rock, volcanic fury, or abiotic reactions, but one tied inexorably to the processes of life. The James Webb Space Telescope had captured evidence of a world so exquisitely tuned, so brimming with the markers of vitality, that researchers attained a degree of confidence seldom achieved in the study of distant planets. Not a tentative hint, not a distant hope, but a planet that stands as fully habitable, and in key ways perhaps more hospitable to life than Earth itself. This finding does not merely imply that life could thrive elsewhere. It indicates that we may have already encountered its unmistakable signature. The revelation emerged silently from infrared observations taken during the planet's transit across its host star. As stellar light passed through the world's atmosphere, certain wavelengths vanished, absorbed by molecules that etched their presence into the spectrum. Initial readings revealed expected compounds: water vapor, methane, carbon dioxide, each one vital, each one intriguing. But then emerged the compound that transformed the interpretation entirely: dimethyl sulfide. On our world, this molecule arises solely from biological sources, not from geological upheaval, electrical discharges, or pure chemistry, only from life. And the detection was robust, sufficient to reduce the likelihood of error to fewer than 3 in 1,000. In a discipline defined by caution and qualification, such assurance represents a landmark. The world-designated K218b circles a cool red dwarf star, 124 light-years distant, positioned precisely within the zone where liquid water can persist on a surface. Yet it defies the archetype of rocky, Earth-analog planets long considered the prime targets. This is a Hycean world, larger and more massive, enveloped in a deep hydrogen-helium atmosphere, overlying what models suggest is a global ocean. Far from rendering it uninhabitable, this configuration may render it exceptionally suited for sustained biology. K2-18b does not teeter on the precarious edge that defines Earth's climate. Its conditions appear profoundly resilient. Surface temperatures are estimated near comfortable levels for liquid water, moderated to avoid runaway evaporation or freezing. This equilibrium stems not from chance, but from the insulating properties of its thick atmosphere, which distributes heat uniformly around the planet. Even on the hemisphere eternally facing away from its star, tidally locked in perpetual twilight, the environment remains conducive to oceans that neither boil nor solidify. The planet's greater mass, roughly 8 times that of Earth, confers surface gravity about 2.5 times stronger. Yet this proves advantageous. It securely retains the voluminous atmosphere, averting the gradual loss that stripped Mars of its air eons ago. What might seem daunting to human physiology becomes a safeguard for longevity. Enhanced gravity, dense atmospheric blanket, even thermal distribution. These elements forge a setting where life need not perpetually contend with existential threats, allowing it instead to proliferate, diversify, and refine over vast epochs. The parent star, a red dwarf, is diminutive and temperate compared to the Sun, yet possesses extraordinary endurance. Whereas our star will one day swell and consume the inner worlds, red dwarfs maintain stable output for trillions of years. Thus, any biosphere on K2-18b enjoys an almost boundless timeline for development. Completing its orbit in just 33 days, K218b resides close to its star, yet absorbs stellar energy comparable to Earth's insolation. This placement anchors it firmly in the habitable zone, but with enduring prospects far exceeding those around Sun-like stars. The extended lifespan of the habitable zone for red dwarfs, combined with the planet's atmospheric shielding against flares and uniform heat redistribution, compels a re-evaluation of habitability criteria. This observation implies that traditional Earth-like worlds may not represent the optimal venues for life. Rather, the cosmos may abound with larger, ocean-dominated planets that offer greater stability and resilience. What elevates this detection beyond mere potential is the atmospheric composition's profound disequilibrium. The coexisting gases, methane, carbon dioxide, water vapor, and notably dimethyl sulfide, defy abiotic expectations. Without ongoing replenishment, they would react and dissipate toward equilibrium. Yet they endure in abundance. On Earth, such imbalance is sustained exclusively by biotic processes, photosynthesis, respiration, microbial cycles that incessantly renew atmospheric components. K2-18b exhibits analogous dynamics. The conspicuous depletion of ammonia, which should abound in hydrogen-dominated lifeless atmospheres, further bolsters the case. Some process is actively consuming it, a process most plausibly biological. If validated, this signifies not a world primed for future life, but one where biology already exerts planetary influence, its chemical byproducts diffusing into the atmosphere and imprinting on light traversing 124 light-years. For generations, exoplanet research adhered to a narrow paradigm. Life demanded near-perfect replicas of Earth, similar radius, composition, thin nitrogen-oxygen envelope, orbiting a solar twin. K2-18b upends that doctrine comprehensively. It bears no resemblance to Earth's sibling. It is a broader, deeper oceanic realm governed by principles once deemed antagonistic to biology. Its substantial mass and hydrogen envelope, previously dismissed as barriers to surface habitability, now appear as enablers of enduring liquid water worlds. Strong gravity prevents atmospheric escape. The thick envelope buffers radiation and evens climate. This shift reorients the field. True habitability may prioritize durability over delicacy, mass over moderation, permanence over precarious equilibrium. K2-18b posits that the galaxy's most conducive environments are not fragile terrestrial clones, but fortified Hycean oceans built to persist across cosmic timescales. Beneath the hydrogen veil of K2-18b extends what could be among the most vast aquatic domains imaginable. A globe-encircling ocean, potentially kilometers deep, where water interfaces directly with high-pressure layers influenced by dissolved gases. This is no segmented sea bounded by continents, but a continuous, planet-spanning fluid sphere dwarfing Earth's combined oceans. Hydrogen integration alters water's properties profoundly, broadening the pressure and temperature windows for liquidity and enabling stability in regimes inaccessible on Earth. Extreme depths that would crush unprotected biology here become viable through buffered chemistry. This unlocks prospects for stratified biospheres of staggering vertical extent, surface layers exchanging with the atmosphere, mid-depths harnessing chemical energies, abyssal zones thriving on internal heat fluxes. Evolution in such abundance would accelerate, unhindered by resource limitation or surface constraints. The intensity of the putative biosignature compounds astonishes most. Dimethyl sulfide degrades swiftly under irradiation. Its persistence on Earth demands continual production, chiefly by marine phytoplankton across expansive seas. For Webb to register it across interstellar distances, replenishment on K2-18b must be prodigious and widespread. This precludes isolated pockets of microbes. It demands oceanic biology dominating global chemistry. Not tentative emergence, but a mature ecosystem exhaling its metabolites into the sky. The atmosphere functions as an extension of the biosphere, maintained far from equilibrium by relentless biological throughput. K2-18b does not simply permit life, it is profoundly altered by it. The broader ramifications cascade outward. Red dwarfs constitute over 70% of the Milky Way's stellar population. If a meaningful fraction host Hycean analogues to K2-18b, habitable candidates multiply exponentially, not incrementally, but by orders of magnitude. Planets once marginalized as oversized gas-enveloped oddities reclaim centrality in the hunt for life. The galaxy may not harbor scattered terrestrial rarities, but teem with ocean worlds, each shielded by enduring atmospheres, each afforded trillions of years for biospheres to mature beyond Earth's adolescence. K2-18b compels an audacious inference. Life may not be anomalous where conditions permit water, energy, and duration. It may be inevitable. And Webb has furnished humanity's clearest vista into that abundance. Hydrogen atmospheres were long viewed as evolutionary cul-de-sacs, too fugitive and reactive. On Earth, the gas flees rapidly. On K2-18b, it prevails, forging a massive thermal regulator that eradicates extremes. It does not passively overlay the ocean. It actively moderates radiation, pressure, and energy flow. Infrared trapping is superlative, abolishing diurnal or seasonal swings. The planet experiences perpetual moderation. Biology faces no imperative for constant stress adaptation. It gains liberty to elaborate form, scale, and interdependence. What was branded inhospitable reveals itself as the premier cradle for flourishing.